Okay, so let's see about physical quantities. Okay, what I mean by physical quantities. So basically, physical quantities are quantities that can be measured. Okay, for example, okay, we can take mass. Okay, so for example, the mass of a man is 75 kilogram. Okay, so 75 kilogram is actually represent the mass, right? And then so what is mean by 75 and what is kilogram? So 75 is actually okay, magnitude. Magnitude. Okay, magnitude. Okay, and whereas kilogram is actually the unit. Okay, so the unit for mass is, in this case, is kilogram. Okay, and then 75, the value, I mean the number is actually the magnitude in this case. Okay, and then what is m? M is actually the symbol, okay, of the quantity. Okay, so if you take a physical quantity, okay, it basically consists of symbol of the quantity, okay, magnitude, and also unit. Okay, let me give you another example. The distance from okay, Ayatawa to Setiawan, okay, is 13 kilometer. Okay, so in this case 13 is actually the magnitude. Okay, magnitude. Okay, kilogram, sorry, kilometer is actually the unit. Okay, and then okay, for distance we can use S as the symbol. So in this case, this is the symbol, symbol for distance. So I think you are clear with what I mean by physical quantity. So basically, physical quantities are quantities that can be measured. Okay. Okay, so there are two types of units for any physical quantities. Okay, which is imperial unit. Imperial unit. Another one is metric unit. Okay, so if you take length, the imperial unit is okay inches. For distance, it can be mile. Okay, and then if you take metric unit for length, the metric unit is okay centimeter. Okay, millimeter. All these are the metric units. Okay, and of course meter and so on. So metric unit. For distance, okay, we will be using kilometer. Okay, kilometer. Okay, if we take what they call mass, mass, the imperial unit is pound, whereas the metric unit is kilogram. Okay, so the one that we commonly use in our okay daily lives, right, is more to metric units. Okay, we are okay what do you call not using much imperial units. Okay, so it become less popular. Okay, is that okay? But sometimes we might be using like inches, okay, feet, okay, and all this, right? But nowadays these units are actually coming less popular. Okay, more to metric units. And then we have what we call as SR unit. SR unit. This is very important lah, in science. Okay, so what is SR unit? SR unit is actually, okay, a standardized measuring unit which is used worldwide. Okay, and then the main reason for this standardized measuring unit is we want to standardize the measurement of the units in scientific field, medical field, commercial, sports, okay, to be more convenient. Okay, for example, if you take what you call length, we'll be using like meter, centimeter, right? And then for, okay, sorry, SI, when you come to SI unit, the length is actually measured using meter and not centimeter. It must be in meter. Okay, and then when you come to time, we'll be using, okay, seconds. And for mass, we'll be using kilogram, and then for current, we'll be using ampere. Okay, so this is for, okay, length. This is for time. This is for mass, and this one is for current, electric current. Okay, and physical quantities can be okay, categorized into two. Okay, the first one is base quantity, and the second one is derived quantity. So what I mean by base quantity? Okay, base quantities are quantities which cannot be derived from other physical quantities. Okay, for example, mass, length, and time. Okay, whereas derived quantities are quantities which are obtained by combining base quantities by, okay, multiplication, division, or combination of these two operations. So meaning in order to get this derived quantity, we might be using multiplication and also division, both together. Okay, and now another important thing is the unit, okay, for this derived quantity is also combination of the base quantities used. Okay, so later we'll be okay, looking at some of the examples, okay, how we can derive the unit of a derived quantity. Okay, so formulas are used to describe derived quantities in terms of base quantities. Okay, from the formula unit for the derived quantities in base unit can be obtained. Okay, so for example, let's say we take density. Okay, density is a derived quantity. The formula, okay, for the formula for density is given by rho. Rho is actually the symbol that we use for density. Okay. Okay. Mind. Let me erase this. I want to write down this in words first. So density is actually equals to mass over volume. So when we write this in terms of the what you call symbols, it's going to be rho m over v. Okay, m over v. Yeah? Okay, so what is m? M is mass. Okay, so if you want to rewrite this in terms of the base quantities, rho is going to be m. So m is already a base quantity, so you cannot change anything, so you have to use m, which is mass. But volume itself is a derived quantity. So how we get volume? Volume is basically, okay, length multiply with, okay, width multiply with the height. Okay, so in this case, length, width, okay, height, everything is related to length, right? So I'm going to use L times L times L. Okay, so when you write this in terms of base quantity, you're going to use L for all the three what you call quantities, which is length, width and height. Okay, so how to get the SI unit? So in order to get SI unit, what you have to do is we take the unit of the mass. The unit of mass is kilogram, okay, and then we divide with the, okay, unit of volume. So what is the unit of the volume? Okay, for the length is centimeter, sorry, for SI unit is meter, so meter. For width is also meter. The unit for height is also meter. So when we simplify this, we will get, okay, kilogram, okay, over m cube, and this can be written as kilogram meter power of -3. And then how you read this? You will be reading this as, okay, kilogram, okay, per cubic meter. Okay, kilogram per cubic meter. The power of 3 you read as cube, and power of 2 then you read it as square, right? Okay. Okay, now base quantities. So let's look at base quantities first. So in your syllabus, you're going to study about, okay, 7 base quantities. 7 base quantities. The first one is length. The second one is mass. Okay, and then we have time. Okay, electric current, absolute temperature. Okay, luminous intensity is related to light. Okay, and then quantity of matter. Okay, the first one, okay, length. Okay, so what is the quantity symbol for length? It's actually L. I already introduced to you earlier. Okay, so it's actually L. And then for mass is M. Okay, for time, okay, small t. Electric current is capital I. For absolute temperature, it's going to be capital T. Okay, and then luminous intensity is I, and then you have a, okay, subscript V, and then we have N for quantity of matter. Okay, and let's look at the SI unit for each of these base quantities. First of all, length is meter. For mass is kilogram. For time is second. For electric current is ampere. For absolute temperature is Kelvin. And then for luminous intensity is candela. Okay, candela. And then for quantity of matter is going to be mole. Okay. Okay, next, the respective symbol for SI unit, or SI unit symbol. Okay, for meter is of course m. So don't get confused with the okay what you call SI unit symbol for length with the quantity symbol for mass m. Okay, so sometimes we might be using the same letter to represent different things. Okay, so we have to be careful. Okay, kilogram for kilogram, so kg, kg for kilogram, s for second, and then capital A for ampere, capital K for Kelvin, and then CD, okay, for candela, and then mole for mole. So I have to remember the what they call the SI unit for each of these base quantities. Okay, remember these base quantities cannot be okay obtained or derived from any other base quantities. Okay, next let's look at some of derived quantities. Okay, the first one is going to be area. So the formula for area is A, okay, equals to length multiplied width, so which I'm going to write this as L square, and then volume V is equals to length multiplied with width multiplied with height, so it's going to be L cube. Okay, and then density, as we already discussed earlier, the formula is rho equals to m over capital V. Okay, now how about velocity? Okay, the small v is equals to length divided by time. Okay, velocity is actually rate of change. Okay, velocity is actually rate of change in displacement over time. Rate of change in displacement with time. Okay, so displacement is represented by L, and then time is represented by T. Okay, next, momentum. Momentum is actually the product of mass and velocity, so it's going to be mv. Okay, product means is multiplication. When it's come to rate, then it will involve division. Normally whatever known as rate must be divided by time. Okay, next, acceleration. Acceleration is actually rate of change in velocity. Okay, so as I told you earlier, it's going to be v over t, because it's rate, so we write over t. Okay, next, force. Force is actually a product of okay mass and acceleration, is ma. And next, pressure. Pressure is given by normal force. Force is going to be F, capital F. Okay, pressure is normal force per unit area. So per is EY, so area is capital A. Okay, now let's look at the relation with the base quantities. Okay, so meaning we're going to express this formula okay using base quantities. Okay, the first one, L square is going to be L multiplied with L. Okay, and then L cube is going to be L multiplied with L multiplied with L. Okay, and then density, as we already discussed earlier, is going to be m over volume. Volume is L times L times L, so L times with L times with L. Velocity is L okay, divided by t, okay, because velocity is made of displacement and time, both are base quantities. Okay, next, momentum. Okay, momentum is mass multiplied with velocity. So mass, of course, mass lah, we cannot do anything about it. But velocity, what is velocity? Velocity is, in this case, okay, uh, L over T, right? So we write L over T. We just use the information that we already got earlier. Okay, next, acceleration. Take V is actually L over T. And now what we need to do is we have to divide this with another T. Okay, so when you do that, you're going to get L over T times T. Okay. Okay, next. Okay, force. Okay, force is, okay, M times A. M is of course M, and then times with A. What is A? A is actually L over T times T. So you can rewrite this as ML over, okay, T times T. Okay. Okay, the next one. Okay, pressure. Pressure is force over area. For force, we're going to use ML over T times T, and then this is again divided by what? Divided by A. A is actually L times L, right? Okay, so L times L, L times L. It will become like this: ML over T times T divided by, okay, L, okay, L, and later become ML T times T times with, okay, 1 over L times N, L times L, cancel one of those L's. Okay, and then what we get in the end is actually M over, um, T times T times L. Okay. Okay, so anyway, I'm going to erase all this and then just replace it with this one. Okay, now so in terms of the base unit, okay, so if you refer to, okay, relationship between the base quantities, actually you can derive the base unit L times L. So for L is going to be M, okay, multiply with another, okay, M times M. So what you get here is, okay, sorry, okay, I just formatted my laptop yesterday. So I couldn't manage to update my software, so I have some difficulties here. Okay, so m times with m, so you get square meter. Next, m times m times m, so we get cube, cube meter. Okay, next, m is actually kilogram. The unit for mass is kilogram, and then L times L is actually m cube. Okay, so what we get here is kilogram per cubic meter. Okay, for L is actually meter divided by the unit SI unit for time, which is second, so we get ms power of -1. Okay, mass is kilogram multiply with the unit for velocity, which is ms -1, so we get kilogram meter per second. For acceleration, so we take the unit for what you call velocity, which is ms power of -1. We call this as meter per second. Divide by time, which is where the unit is s. So we get ms power of -2. Next, force is mass times with acceleration. The SI unit for mass is kilogram. We multiply with the SI unit for acceleration, which is meter per second per second. Okay, repeat again. It's meter per second per second. So what we get here is kilogram meter per second. Okay, and the last one, we take the unit for force, which is kilogram meter per second divided by the SI unit for area, which is square meter. So what we get here is kilogram. Okay, we will cancel out one of those m, right? So what we get here is m to power of -1, s to power of -2. Okay, and some of these derived quantities have their special SI unit. Okay, not all, some. Okay, for example, we take force. We take force, the special SI unit is actually Newton, which can be written as capital N. Whereas for pressure, it's going to be Pascal, which can be represented by capital P. For rest, the special SI unit doesn't exist. So we're going to use square meter for area, cube meter for volume, kilogram per cubic meter for density, meter per second for velocity, kilogram meter per second for momentum. And then for acceleration is meter per second. And one more thing, sometimes we might have equivalent units. For example, if you take momentum, actually we also can use, okay, Newton second, Newton second, okay, Newton second, okay, Newton's, this is actually equivalent to ns, okay, Newton second. Okay, if you multiply kilogram per meter, kilogram meter per second with second, you're going to get kilogram meter per second. Okay, what I mean is this one. Okay, from here to here, we take kilogram meter per second, we multiply with an s, then the whole, this whole thing, right, can be replaced with n, and then you have a s. Okay. Okay, so far any questions? So actually you can copy all this in your workbook. Okay, you can look for this table in your workbook. Only F magnitude. Okay, no direction. Vector quantities. Okay, as both magnitude and direction. Okay. So example of scalar quantities are area. So area doesn't have what you call, okay, magnitude. Sorry, area of magnitude. All these quantities will have magnitude. Okay, area doesn't have direction. Same goes with volume. Volume also no direction. Okay, density. Density also doesn't have direction. Temperature also doesn't have direction. What else? Okay, time. Time also doesn't have direction. Okay, and then you can continue with what you call, okay, pressure. Pressure also doesn't have direction. Pressure. Okay, work. Okay, energy. Okay, and then the list actually goes on. Okay, whereas when it's come to, okay, vector quantity, okay, we have a displacement. Okay. And then we have velocity, acceleration, momentum, okay, and of course force. So all these quantities actually have direction. Okay, in the next chapter we'll be studying in detail about, okay, this what they call vector quantities. Okay, together with the calculation related to these quantities. Okay, so remember, for vector quantities, there's what they call magnitude and direction. So direction is very important for vector quantities. Okay. So I want you to go through the descriptions that given here, or the situation that given here, and then identify the quantities that involved. Okay, look at the first one. Okay, a ball of mass 1.2 kilogram is dropped from a table with a velocity of 2.0 meter per second. So remember, okay, you have to look for physical quantities. What is physical quantities? Quantities that can be measured. Okay, so what are the quantities that can be measured in this case? Okay, mass. Mass is, okay, the first quantity that you can find here, and then velocity. In the second okay, event, we have a temperature. Okay, in the third one we have mass, we have what they call acceleration, we have initial velocity. Okay, velocity, yeah. Okay, and the last one, power. Okay, and then we have mass. Okay, so now let's categorize them into base quantities and derived quantities first. So this is mass. Okay, mass. And then derived quantity is velocity. Okay, in this event, the second event, there's only one quantity. So that quantity is actually base quantity, yeah? Temperature. Okay. In the third event, mass is the base quantity, acceleration and velocity are derived quantities. Okay, next. Power. Power is actually a derived quantity. Mass, as usual, is going to be base quantity. Okay, and okay, let's categorize these quantities into scalar and vector. Okay, scalar, mass is going to be scalar. Okay, temperature, scalar quantity, mass again scalar quantity. Okay, okay, both mass and power, okay, are scalar quantity. Power is also another scalar quantity. There's no direction for power. Okay, so next, in the first event, velocity is going to be the vector quantity. There's no vector quantity in the second event. In the third one, both acceleration and velocity are going to be vector quantities because it involves direction. Okay, in the last one, there's no vector quantity, so we just put a dash. Okay, so far any questions? Okay, so the relationship. Okay, first of all, let's interpret the shape of the graph. Okay, the graph is actually a straight line. First of all, it's a straight line. Straight line. and then it, okay, y-intercept is actually 0. What is y-intercept? Is this one, the location where the graph cut the y-axis is known as y-intercept. So y-intercept is 0. So when you get a straight line, okay, and then the y-intercept is 0, and next the gradient is positive, okay, m is positive, okay. So the m here, right, so in this case m represent gradient of straight line, okay. So gradient is positive. Positive gradient, there are 4 types of straight lines, okay. The first one, positive gradient, the line is inclined towards right, okay, positive gradient. The second one, okay, positive gradient. The second one is inclined towards left, okay. Negative gradient, okay. The third one is actually, okay, horizontal line, okay. The positive gradient, you have a negative gradient, and this is zero gradient, and the last one, number 4, for vertical line, the gradient is infinity, okay. So for a straight line with a positive gradient and with a y-intercept 0, or we call this as, okay, pass through origin, then the relationship is actually going to be, okay, directly proportional. But you cannot just write directly proportional, you have to write in complete center like this: y directly proportional to x. Okay. Okay, next. This is a straight line. Okay, straight line, positive gradient, but the problem is the y-intercept. Okay, y-intercept also can be given by the letter c, small c. Okay, c is not 0. So in this case, if you look at the graph, right, it doesn't pass through 0. Okay, so the difference between the first line to the second one, okay, is the y-intercept. So y-intercept is not 0. So the relationship is going to be y increases linearly with x. Again, next, we have a straight line. but now the gradient is negative, and then the y-intercept is also not equals to 0. So what is the relationship? The relationship is y decreases linearly with x. Okay, now let's look at the equation for all these three graphs. Okay, the first one, y equals to mx. Okay, m is the gradient, and from where you get this y and x, y is from the y-axis and x is from the uh, horizontal axis. Okay, because we already learned in modern maths, the equation of a straight line is y equals to mx plus c, yeah? And y is, okay, the quantity for the vertical axis, x is the quantity for the horizontal axis, m is the gradient, okay, gradient of the straight line, and c is the y-intercept. So in this case c is 0, so we can just ignore the c, yeah? Okay, for the second graph, the equation is y equals to mx plus c. Okay. The third one is also same, y equals to mx plus c. Only thing is, this m is going to be positive, but this m is going to be negative. Okay. Let's move to the next one. Can someone answer me? Can you see the screen?
Yes.
Okay, good. Okay, so look at the first graph in this page. The relationship between x and y is inversely proportional. Okay, the first graph, right? The first graph here is not a straight line, it's a curve. Okay, when x increase, y decrease. Okay, so the relationship between x and y, okay, inversely proportional to x. Okay, and then this graph also can be converted into a straight line. I mean, this relationship can be converted into a straight line graph by, okay, changing this x into 1 over x. Okay, so by just changing the what you call the quantity of the what you call horizontal axis into 1 over that quantity, we will get a straight line graph. Okay, so the equation for this relationship is actually y equals to, okay, k over x. Okay, or we also can write this as y equals to k 1 over x. So if you take the second graph, right, okay, the k is actually going to be the gradient of the graph. Okay, next. So the relationship, okay, for this case, y increase, okay, increases with x. Okay, because if we notice, when x increase, y also will increase. For example, let's say we take two values on this graph. Let's say this is 1 and this is 2. When x is 1, maybe this is like, okay, 5, right? And then when it's 2, maybe you get 9. Okay, so what happened when x increase from 1 to 2? Y is also increased from 5 to 9. So x increase, y also increase. x increase, y also increase. Okay, let's look at the second one. For example, let's say I take this as 1. Okay, maybe this is 2. So let's assume this is 3. Okay, maybe this is like, okay, 5. Okay, so when x increase, y is also increase, but the rate, okay, of the increment is actually not proportional for both of these graphs. Okay, so that's why we just write y increase with x. Okay, okay, next. When x increase, what happened to the y? Okay, for example, let's say we take this as x equals to 1, the value of y may be 10. Okay, what happened when x is around 5? Okay, the value is maybe just sorry, cannot be 8, right? Doesn't make sense. Okay. Okay. So here maybe it's like 4. So when x increase from 1 to 5, what happened is y decrease from 10 to 4. So y decrease. Okay, so the same thing is applied to the second graph. Y decrease, but the rate of the reduction is actually not same. Okay. The relationship is y decreases with x. Okay, so for the what do you call the last two graphs, right? So I mean okay, so initially already given, okay, what do you call, okay, 3 graphs. So this is going to be number 4, number 5, and number 6. Okay, so for number 5 and 6 you don't need to worry about the equation. Okay, because graph number 1 until 4 is involve straight line, right? Or it can be represented using straight line, even though like inversely proportional graph, right, originally is a curve, but it can be converted into a straight line. So we can write the equation for graphs related to straight lines. The one which is not a straight, or the one with a curve, we are actually not interested with the equation. Okay, so there are like 5 important things when we want to analyze a graph. Okay, the first one, we interpret the shape of the graph, like what we done earlier. Okay, so why we need to interpret the shape? We want to get the relationship between the variables. So the relationship can be directly proportional, inversely proportional, increasing linearly, decreasing linearly, and so on. Okay, and then okay, we calculate gradient and determine the physical quantity that represented by the gradient. Okay, this is more to straight line graph. And then okay, uh, the next one, we might calculate the area under the graph. Okay, area under the graph, and then determine the physical quantity represented by it. Okay, so remember, not all the graphs we can find the area. Okay, actually you can find the area, but sometimes the area under the graph is meaningless. Okay, so in future you will learn where in some cases when you calculate the area, it actually doesn't bring any meaning. You can find the area, but it doesn't bring any meaning because it doesn't represent any quantity. Okay, if the area represents some sort of quantities, then it meaning lah. There's a meaning for that value. Okay, otherwise it's meaningless. Okay, and then we can find the physical quantity by interpolation or extrapolation. Okay, so definitely you have learned about these two techniques, interpolation and extrapolation. Okay, so later we will be discussing the question related with all these five things. Okay. Okay, wait. Okay, never mind. Okay, look at this one. Okay, so earlier we already see about the relationship between the variables based on the shape of the graphs. Now let's see how to find the gradient of a graph using what do you call? So not using for straight line graph. Okay. So the formula that we're going to use in this case is gradient. Gradient is equals to y2 minus y1 over x2 minus x1. Okay. So first of all, you have to draw a triangle, a right angle triangle with a minimum size of 8 centimeter by 8 centimeter, meaning 4 big boxes. Okay. So in this case, this is like what you call one big box. So this is like one big box. Okay, this is also one big box. So in this case, if you want to get minimum size of 8 by 8, so at least like you have to take 1, 2, 3, 4. Okay. Okay, maybe you can take this as a triangle. Okay. But the most important thing is the horizontal one must be 4 lah. In the case the vertical one you couldn't get 4 big boxes, but in this case there's no problem. You can easily get a minimum size of 4 big boxes. Okay. So first let's construct. So I'm going to take, actually you have to use a ruler. So take the ruler, draw a vertical line, and then a horizontal line, okay, mark 90 degrees. Okay, mark 90 degrees to show your right angle triangle. Okay, especially when you are using a pencil to draw the graph. Okay. Okay, next let's identify the coordinates. So the coordinate here is 0, 0. The coordinate of the last point is 100. Okay. And the value here is Okay, we have 1 2 3 4 5. Okay, 5. It's going to be like, okay, 2.75. 2.75. So let's use the formula to find the gradient. M for gradient is equals to y2. This is y2. This is x2, x1, y1. So 2.75 minus 0 over, okay, 100 minus 0. Okay. So this will give us 0.0275. Okay. Right. And then how to find the unit? Okay, very easy. We take the unit of the, okay, vertical axis and the unit for the horizontal axis. Unit s square divided by, correct. Okay, the unit of the vertical axis we divide by the unit of the horizontal axis. So the gradient is going to be 0.0275 s square g to power of -1. Okay, I hope you can understand why it becomes g to power of -1. Because it's over g, right? So when you, okay, based on the law of indices, for example, if they 1 over a is going to be a to power -1. 1 over a squared, then it's going to be a to power -2. 1 over a to power n is going to be a to power -n. So, okay, this is law of indices. Okay, so we are done with this. Okay, so characteristic of graph. Okay, so when you draw a graph, right, there are several important things that you have to remember. The first one, okay, you must make sure you have labeled the axes correctly. Okay, next, make sure you write the unit if there's a unit. Okay, number 2, unit. Okay, number 3, the what it calls scale. The scale must be even. Okay, so even scale means is like 1 to 1, 1 to 2, okay, 1 to 5, 1 to 10, 1 to 100. Okay, so it can be like in the multiple of okay, 10 or multiples of 100, sorry, tens, meaning it can be like 1 to, okay, 0 0.1, 1 to, okay, 0.01. Okay, all this can be used. Okay, and then we also can use 1 to 2, 1 to 5, but don't use 1 to 4. 1 to 4, okay, not recommend. Okay, okay, not recommended lah. Okay, don't use 1 to 10, 1 to 3, okay, don't use 1 to 3, okay, 1 to 6, okay, don't use all this. Okay, next, uniform. What does it mean by uniform? The increment must be same. For example, from here to here is 20, from here to here is also 20, from here to here is also 20. Okay. The same thing is applied for the vertical axis. The difference here is 0.5. Okay, and then same goes with the rest of the values. Okay, but the increment for the vertical axis and the horizontal axis, okay, not necessarily must be same. It can be different. And then title of the graph. Okay, so title of graph is going to be like graph of t square. T square is actually for vertical axis, from vertical axis. So the quantity for the vertical axis must be written first. Okay, and this is for from horizontal axis. Okay. Okay, next, when you draw the graph, okay, the size of the graph must be at least, okay, 10 times 10 centimeter by 8 centimeter, meaning it must be like 5 times 4 big boxes. Okay, just now I already explained to you what is mean by big boxes. Okay, I mean this is counted from the first point to the last point. So meaning in this case, this is the first point and this is the last point. So if you count, we have 1, 2, 3, 4. Okay, so the minimum size is accepted. Okay, but don't just draw the line to connect the first line to the last line. Make sure the line that you draw, okay, touch the vertical axis, or in other words, it touch the y-axis. Okay, and draw the line of best fit. What I mean by line of best fit is your line must pass through as many as possible points. Okay, and then the number of points above the line and below the line must be balanced. So let's say you have 1 point above the line, 1 point below the line. Okay, 2 points above the line, 2 points below the line. But that case doesn't happen because for your syllabus, normally when you what you call, when you tabular the values, okay, you only take 5 points. Okay, so when you have only 5 points, okay, so you won't have cases like 2 points above and 2 points below. In that case, there's only 1 point on the line. Okay, so at least there must be like, okay, 2 or 3 points on the line. Okay, and then the line that you draw must be sharp and smooth. Okay, so these are the important things when it comes to drawing the graph.